So thank you so much for the very kind introduction. I'm super excited to be here to discuss some of the work we have been doing on learning structured world models of the environments from the robot's physical interaction with the environment and for the robot to do better physical interactions. The goal of today's talk is that by building a model with some prior from our understanding of physics, we can have this kind of modeling techniques allow the robots to do very complicated deformable object manipulations in the real environment. So first of all, we want to ask the question, so how far are we in achieving this kind of human level manipulation capabilities? So many of the existing systems in the real environments in the industry are mostly focusing on objects with relatively simple shapes for relatively simple pick and place tasks. But we humans can do much more than that. We can crack eggs, spread butter on a piece of bread, making dough, and making sushi. Many of these capabilities goes far beyond the reach of the current robotic systems. So one of the key enabling factors for doing this deformable object manipulation is this intuitive models of the world. We have this model in our minds. We can predict how the environment is going to change if we apply a specific action. For example, how the dough will deform and how the onion pieces will move around. And it's exactly this predictive ability that allows us to plan our behavior to achieve a specific targets. Here's how the framework looks like. We have a planner that taking the observation from the words and generating actions. And there will be some internal intuitive models that will do the predictions of the results of the actions. And this is essentially a type of predictive model. In order to build this type of predictive model, there are generally two ways of doing this. One is all the way trying to learn the model from observations. Many people categorize it as sometimes 2D world models. The general idea is take the visual observation and learn the dynamics model either directly over the observation space or over some kind of latent space. The nice thing about this approach is can directly learn from partial observations and handle systems where the underlying dynamics are uncertain or unknown. We have successful examples like Mu0 or controlling robots from pixels. But the challenge of this approach, it is very unstructured and very limited in terms of generalizations. For example, when humans looking at the, for example, Play-Doh or coffee beans, we are not thinking of them as just one single latent vectors. We have some structured understanding of those objects for us to generalize to these objects. Talking about the structure, the other way to build a dynamics model is based on our understanding of physics, like F equals ma. This is arguably the most structured ways of building the model and has excellent generalization. We also have a lot of very successful examples, like building models for the humanoids, for the planes, for the rockets. And we have beautiful results by doing very a rigorous understanding of the model and doing planning based on the model. But this type of approach typically require you have full state information of the environments. And you need the full state estimation and parameter identification. This is sometimes very hard or nearly impossible for many real-world manipulation tasks. For example, for the pile of onion pieces, it's just impossible to estimate the geometry and pose of each and every one of the onion pieces. Or buttoning our shirts, we human only have to know the local information before we can do these tasks. So both approaches have their advantages and limitations. The left is model learning, and the right is structures in the model. So my research really trying to bridge the gap and get the best of both worlds, trying to learn models with structures inspired by understanding of physics, and using the model learned directly from the real-world interactions, and for the robots to do better physical interactions with the environments. So subsequently, I will first review some of the earlier works we have been doing, especially on the directions of building graph-based neurodynamics model. And on the later half of today's talk, I will be discussing some of our recent investigations on trying to thinking more broadly in incorporating more physics or more learning along the different fronts. So let me first define the problem, make it a little bit more concrete. So we want to optimize an objective function C, defined over the observation Y and also the action U. We have to think through three most critical constraints. The first one is perception. It essentially maps the observations into some representation of the environment Z. Then we have the dynamics model that predicts how the Z will evolve as a result of input actions. Then is the control. It essentially maps the Z into some action that can minimize the objective function. If you look carefully at this formulation, the choice of Z play a very profound impact on the structures of the overall systems. And the selection of Z has to be very carefully determined. And that will determine essentially like the generalization capability of your systems, and also the sample efficiency of your systems. So for many of our work, especially in the field of deformable object manipulations, we use particle as a representation, which essentially decompose the objects into a bunch of small points. And we use graph to model the interactions both within an object and across different objects. This is some of the very fine-grained ways of modeling those objects. So in order to model the particles interactions, we use graph neural network, and we call it graph-based neurodynamics models. So many of you might have already been familiar with GNN, but just a quick recap. So we have a graph of 3 nodes and 3 directed edges. Our representation Z is the union of the node set V and the edge set E. And for each edge going from point B to point A, we'll have an edge encoder that's taking the sender information and receiver information to generate the representation for that specific edge. And then for all the nodes inside this graph, we will aggregate all the representations on edges where node A is the receiver. And together with the information on node A, we'll be able to update the representations on node A. And then we can define any objective function you care to supervise this model. For this case, what we care is the evolution of the systems. So we'll be able to minimize the objective, measuring the difference between the predicted outcome and what actually happens in the real environments. So one thing to note about this model is that the edge encoder is shared among all edges, and node encoder is shared among all nodes, such that the NERD model can naturally generalize to systems that are larger or smaller than during training. Here are just some quick results of the trained model. On the left is the ground truth. On the right is our model's open loop predictions, meaning the inputs are only the position and velocities of all particles at the first frame. Here's another example where we have 2 cuboids to mimic the 2 fingers of a parallel jaw gripper. Here's another example of shaking a box of fluids, where the inputs are the initial states of the particles as well as the subsequent sequence of the actions. And like I mentioned, the NERD model can naturally generalize to systems that are larger or smaller than during training. So when we evaluate the model on scenarios that contains 2 times more particles than during training, the NERD model can still produce very nice results. We are also deploying these systems in the real-world environments. Example including, for example, box, ropes, granular objects, and clothes. We'll be able to show that by abstracting the real-world observations as a graph, we'll be able to use this graph-based neurodynamics model to model their interactions, and we'll also be able to adapt to different material properties like stiffness. And we also want to challenge ourselves. So we tackle some of the challenging, like some of the most challenging, like a deformable object manipulation, which is trying to make a dumpling out of a dough. This is actually a Best System Papers awards like we got at CoRL in 2023. The idea is we build this type of setup, which including 15 different 3D printed tools. Given these 15 different 3D printed tools, we have 4 cameras at the corner of the workspace. It gives the robots observations of this environment. And then the robot will have to select the tools from the tool sets and in order to manipulate the doughs into a dumpling. So again, we use the same like a graph-based neurodynamics model and trying to learn the model from only the real-world interactions. In this case, there's no simulation at all. Everything is learned from the real world. And because we're using graph neural network, like I mentioned, all the node encoder and edge encoder are shared among nodes and edges. So we allow some very, very efficient learnings of this neurodynamics model. For each tool, we only require 20 minutes of real-world interactions for the robot to learn a very performance dynamics model. And we compare it with physics-based models like material point methods. We find that even with very extensive system identification, our NERD model from the real environments without the material gap performs much better than state-of-the-art deformable object simulators. Here are our models like open loop prediction results. The first row is our model's prediction. The second row is the ground truth. You can see we use the red points to represent the geometry of the tool and the blue points to represent the geometry of the dough. And the model's prediction aligns very well with the ground truth. Here's another example where we are predicting the dynamics of the dough as a result of the pressing action. There's a third example, we predict the dynamics of the dough as a result of this kind of rolling actions. You can see the areas of the dough is being enlarged. So now we task the models on this dumpling making task. So here is the results. So what's interesting about these results is there will be a person constantly perturbing the robot from doing its job. The robot will be able to recover from these external disturbances. Here in this case, the robot has to make decisions at 2 levels, both at the high and discrete level in selecting which tool to use. And given the selected tools, the robot has to decide what continuous action to take in order to progress into the next task stage. And this kind of decision-making is all empowered by this kind of neurodynamics model that essentially imagining how the shape of the dough will change when you use a specific tool, apply a specific action. And here, the human just so annoying and adding additional stuff, the robot will always be able to take the observations from these environments and be able to be robust to this type of external disturbance. Here, the human coming again, like folding the dough. The robots will just like know that there's not large enough or smooth enough area for it to cut a circle. Here it actually gets really interesting. After the robot cuts a circle, the humans shows no mercy, destroy everything. And the robot knows it has to start from the very beginning in order to like continue with the task. I would say this really shows like the patience and also the robustness of our robotic systems. So in the end, the robot will be able to make a dumpling out of this dough using 15 different 3D printed tools. So besides the elastoplastic objects, we use the same, exactly the same like architecture, this graph-based neurodynamics model, and to see if you can apply to other deformable objects. Here we apply it to granular object manipulations. Here are actually the results. Here we also like abstract the foreground of the environments using a graph, and also learn a graph-based neurodynamics model to predict how the granular pieces will move around when you apply a specific action. We can use this model to plan the robot's behavior to achieving different target configurations. Like you probably already recognize what the target configurations are. It's all the letter shapes from letter A to letter Z. I want to argue this is a non-trivial task that really involves some non-trivial redistribution of the object pieces and be able to align with the fine-grained detailed targets like as specified using a mask of the environment. So besides granular object manipulation, we also like apply this graph-based neurodynamics model on multi-object interaction scenarios. Here we are tackling a stowing task, and this graph-based dynamics model allows us to predict the multi-object interactions involving like rigid objects of different shapes, as well as like deformable objects and also their interactions to allow us to plan this kind of stowing behavior. So to summarize a little bit of the first half of the talk about this graph-based neurodynamics model, the specific structure we are using is to use particle and graph as the representation of the environments, and using this GNN to model the dynamics. It is particularly suitable for objects that are compositional or with high degrees of freedom. Example including elastoplastic objects, granular media, and also multi-object interactions. It comes with 2 major benefits. The first one is generalizations. Essentially can generate systems that are larger or smaller than during training, as in the fluid shaking example. Can also apply to unseen target configurations, like all the letter shapes, letter A, B, C, D, E, F, G. Like during training, the model has never seen those like letter-like target shapes, but still the learned model is able to achieve those targets. The second major benefit is sample efficiency. Like I mentioned in the dumpling making example, we only require 20 minutes of real-world interactions. It allows us to learn a very decent dynamics model for us to do this dumpling making task. So these lines of work inspire like 2 major lines of follow-up work. The first line is trying to learn large-scale graph-based systems, especially in the graphics community. Here are some works I particularly like from, for example, DeepMind, Intel, Stanford, on large-scale particle system simulations, intuitive physics, and also mesh-based systems. Another line of work are about deformable object manipulation. Here are also some very interesting works on amorphous material manipulation, close smoothing, elastic material manipulation, as well as the benchmarking of the robot's capability in doing deformable object manipulation. So then we are asking the question, like we have already showed that the model is capable of doing all different kinds of deformable object manipulation tasks. Is it good enough, or are there much more additional things we have to do? So obviously, like there's many things we still can do, and there's a lot of challenges we still wait to be solved. One angle is how we can apply or extend to more complicated tasks and more complicated objects, and how you can handle not just homogeneous type of interactions, but different objects with different type of materials and how they are interacting with each other, especially in scenarios that are heavily occluded. And how we can scale up this type of model, not just in this kind of tabletop lab settings, but really using in the wild video datasets. Example including like OpenX datasets or Joy datasets, and really going towards this kind of like a structured word model that provides this kind of engine level capabilities for data generations and evaluations. So I take a step back and look at this overall scheme of things. In general, when we want to build this type of model, one end on the left is more physics-based part. There's more structure in the model. On the right, there's more learning that just remove the structure and trying to do pure data-driven approach. I would like to say that our graph-based neurodynamics is somewhere in the middle. On the left end, on the physics sides, there's a lot of like great physics-based simulators, for example, NVIDIA Warp, which we actually are heavy users of. On the other ends, like examples like DreamGen recently been released also by NVIDIA. They're trying to learn this kind of 2D like video predictions, and that can be retargeted to the robots. And both ends will have their issues. For example, on the physics side, you need the full state information of the environments. And on the learning side, many of the existing results only based on like 2D videos. It doesn't have explicitly 3D structure. It's actually quite challenging, not just to retarget to the robots, but generalize to scenarios that are outside of their post-training data. So you're trying to see like, is there something also in the middle that provides us with the recipe that can really scale up? So we are tackling on different fronts about how to represent the objects and what type of structure can we add. The first work I want to discuss is actually this PhysTwin work, which was actually one of the spotlights. The idea is, can we add more physics-informed prior to our model and allow it to have better sample efficiency and generalization? Here are actually the results. On the left, what we are showing are the observations we are given to our robots, which are just a few seconds of real-world interactions. Here we're showing one view, but in total, we have 3 camera views observing the environment. In the middle column, we are showing our reconstructed states. You can also see the color. That means the points are actually tracked. We also have points on the human hands that indicates the reconstructed actions. And then we build this digital twin. What do we mean by digital twin? We want to have both the appearance, geometry, and also the dynamics. So we construct the digital twin and play our reconstructed action on our digital twin in an open loop fashion and render the video. We overlay that video with the original video shown on the left, and the overlay is actually shown on the right of this video. You can see that this overlay is actually very, very accurate with the original video. That shows this kind of resimulations works very well in capturing the appearance, geometry, and dynamics of the objects. And here is actually our optimization framework. In general, we have 3 optimization terms: the geometry, motion, and also the rendering loss, to allow us to reconstruct all spectrums that's needed for us to build this type of digital twin. And obviously, after you have the digital twins, there's many things you can do with it. Here's just a keyboard interface that just teleoperates the 2 graspers, to move the stuffed animal around. You'll be able to render how the environment is going to change when you apply this action. And this type of framework also applies to not just stuffed animal, but many other deformable objects. Example including, for example, clothes, robes, and also another stuffed animal. We also apply it in the robotic scenario. Here we have Gallo teleoperation setup. That is essentially teleoperating this bimanual setup to move the clothes around. So what we are doing here is to record this action and replay the actions in real times on our digital twin in an open loop fashion. I want to emphasize the open loop here, because as soon as the robot gets the observation at the very first frame, the robot is not getting any additional observations from the clothes. The video showed in the screens that essentially open loop generated. We essentially doing the prediction and overlay the rendered videos with the original, with what's happening in the real environment. So here we're highlighting 2 things. One, the reconstructed digital twin is very accurate. And second, the reconstructed digital twin can run in real time. There's nearly no delay of our model's prediction compared to what's happening in the real environment. We also extend this into fully digitalized worlds and trying to show correlations between the simulated world and the real world. On the right, what we are showing is the real interactions between these robots grasping a rope, trying to insert it into a clip. On the left is our digitalized version with our identified digital twins of this rope. And obviously, with this identified dynamics models, we can do some like a very basic, like a model-based plannings to plan the robot's behavior in achieving some specific target configurations, both for the rope and also for the clothes. And here, like still, just preliminary demos about the accuracy of the dynamics model. And the search space of the action is actually highly constrained for us to achieve the target configurations. So this is about adding the physics-based part, like in extending our framework, in making it more sample efficient and more generalizable. So the other ends, we are also asking the questions, can we actually make this graph-based neurodynamics model even more generalizable and adaptable, and potentially one day can scale up to those in the wild data, like droids or OpenX? So then we present particle-grid neurodynamics model. This really actually is motivated by some of the limitations of what we find from the graph-based neurodynamics model. Typically, when you construct those graphs, they require expert knowledge to determine where the nodes are and where the edge needs to be, and how the nodes should connect with each other, and what are some of the attributes on the nodes and also on the edges. Sometimes they can be quite tricky to determine. And also, if you use graph neural network, the message passing within the graph sometimes can be tedious and takes a lot of time and is not efficient enough. And this type of framework is still limited in scenarios where there's very, very heavy visual occlusions. So inspired by the developments of material point methods, that's not just using like a particle as a representation. Instead, they are using a hybrid representation of both Lagrangian representation and Eulerian representation. The Lagrangian representation is essentially using, for example, points of particles where the changes of the environment, meaning the change of the locations of those particles. And Eulerian representation are example like pixels or voxels, meaning the change of the environment indicating the change of the values or densities of those pixels or voxels. So in this case, we provide this kind of hybrid like modeling approach that do this grid to particle propagation and particle to grid propagations in order to do this kind of like modeling. Here are actually the results. Like similarly, we just allow the robots to just randomly place the rope. So obviously for this work, it's more learning on the learning side. So require like 5-10 minutes of real world interactions. And we build a pure neural-based 3D digital twin. Here, our digital twin, obviously, we have the appearance and the geometry. On the left is the appearance and the geometry, which is represented using Gaussian splatting. On the right is our pure neural simulated like simulator. What's interesting is that there's actually a teleoperation interface. The robots are teleoperated through keyboards. So we press WASD to move the N effector around. We can predict the movement of N effector and how it can affect the shape of the rope. It can also be applied not just on ropes, but also clothes, stuffed animal, and also boxes. So for many of you who are familiar with like dynamic Gaussians, I want to emphasize this is not dynamic Gaussian. Dynamic Gaussian is doing interpolation over time. We're doing extrapolation over time. This is like indeed action condition 3D video prediction that predicts the effects of the actions and how the environment is going to change, which you do extrapolation over time. So I want to summarize a little bit. So our lab really trying to build these structured world models. We have a lot of like beliefs. We believe 3D are important. Some levels of structures are important for us to get the right generalizations and sample efficiency. And I would like to argue, currently there's a lot of like companies, like well-funded companies, they're spent huge bucks in doing data collection. What they are collecting is essentially action-conditioned robot interaction data. Thinking about what you need to learn this model or identify those models, what you need is also action-conditioned robot interaction data. If you're only using those data for imitation learning, I would like to argue it's such a waste. There's a lot of information, especially about the dynamics, that can be harnessed from those data sets. And I really want to find the right recipe for us to scale up to really be able to capture the dynamics through this large-scale data collections. And here are our investigations along the board. Some are more on the physics-based side, some are more on the learning side. So that's actually the end of my talk. I want to thank all the collaborators and funding agencies. Without them, it would be impossible to do all the works I have showed earlier. And I'm happy to take any additional questions. Thank you.
Hello, Professor Li. I just saw this talk in your last the structured learning workshop, so I picked up a good word. I keep seeing the like T-1 or T-minus T plus like past information basically included in these dynamics models. I was just wondering, like a lot of these interactions seem quasi-static. They don't seem super dynamic. So I was just wondering how important the past information or velocity information is when you could also like make a Markov assumption that just assumes that the future states only depend on the current shape of the rope or action trajectory.
Yeah, obviously, for many of this dynamics modeling works, we have to have a proper definition of what we mean by states. So our definition, obviously, state is given the current states, the past and future should be independent from each other. So the current state representation needs to have sufficient information for the model to make future predictions. So in nearly all of our works, we will have not just a current frame, but a few frames from the past in order to have a better understanding about the movements like in some kind of history frames. So this typically works in somewhat like quasi-static scenarios. So currently, as you can see, many of the scenarios are still in a more or less quasi-static region. And you are absolutely right. If you want to move to like a more dynamic regimes, like some better accounting for the history and some kind of inference over the dynamic properties will be necessary. But one thing I hope to note is that with a proper physics-based prior, especially the PhysTwin work shown on the bottom right, although the data we use to identify the dynamics models are more or less quasi-static, but after the identification, the model can actually be used in high-speed regimes, although it may not be as accurate, but technically it can be used in those high-speed regimes and provide you with reasonable results. Thank you.
Hi, Andrew. Awesome talk. So I think your work showed that by incorporating these physics model, we can really learn the dynamics efficiently. So I have a question, and it might be like two parts. So first thing is, when you demonstrate these works, they often happen in a pipeline that you first collect a small data set on your custom object in your lab, and then train I guess, object-specific model on it. So, so that is your current setting. So my first question is, do you think we need a model that is able to represent all objects? For example, your PhysTwin use spring mass system, which I guess is not applicable to all kinds of objects, right? And is such a model what we desire? And second is, do you think your current work can be is scalable and can be scaled up to represent all kinds of objects?
So that's very good questions. I hope to like quotes like all models around, some are useful. So here we essentially shows like some of the models we identified with different levels of physics-based priors that is able to provide this dynamics model that helps the robot to do the downstream tasks. Whether we don't care whether the model is with physics or without physics, what we really care, the robot can use this model to do the downstream task. That is always our gold standards. The model doesn't have to be perfect for it to be useful. That's to like answer your question. And second is about your question about, do you want a unified model? Of course we want. Of course we want a unified model that works everywhere. It's just currently we haven't really seen a recipe that just works across the board. That is why we are tackling different kind of recipes, like with more physics, with more learning. What is the most scalable approach that allows us to like extend to those large scale data? And I want to say one thing is that you want to scale up to those data. We definitely want those kind of prior, those kind of structures. But in order to make sure those structure is compatible with the information we can get from the data, there needs to be a good like perception systems that give you in some kind of intermediate abstractions that is compatible with whatever structures you are adding to your models. And I'm very hopeful for that front because currently we have seen many like a foundational vision model that works just better and better, like a foundation pose, single image 3D reconstruction, like a co-trackers, and also very recent ones, foundation stereo. Those all give you some very beautiful results. And for the PhysTwin, the success of the PhysTwin actually heavily relies on the success of single image 3D reconstruction and tracking. So with those information, those abstractions provided by the vision foundation model, I'm actually quite hopeful of having the right structures and be able to scale it up to those large data sets like OpenX or Droid. Thank you.
Hi. So my question is about actions. I think in all of this work, assuming that you have actions along with your whatever form of state you're using. So I guess the question is, is there a way to extend this for cases where you don't have actions, or rather, can the actions be generic enough that you can do it from, like, for example, OXD, where there's some data that has no actions, or at least different types of actions for different types of robots, for example?
This is also a very good question. So action is an essential component of our system. Like all of our model is action conditions. So we need somehow to gather action information from our data sets. So for all work except the PhysTwin, the actions are essentially the robot actions. So we know the robot actions, so we can get the actions. For the PhysTwin, the action we are getting is essentially to track the movement of the human hands and assume that the object won't influence the movement of the hands, but the hands will have causal influence on the dynamics of the objects. So there actually has to be some assumptions for us to actually recover the actions from the videos of just human interacting with the environments. So like how to actually like be able to do the proper reasoning and the action representation learning from in the wild video, I think that's still research questions. And there's a lot of assumptions you can apply. For example, if you can see a robot there, you could assume like wherever the robot is reasonably fully actuated. So it is not influenced by the environment, but the robot influences the rest of the environments. So those type of assumptions can help us to extract the knowledge of those actions. And I think that might be necessary for us to scale up to those large data sets. Thank you.